Hello again, physicists. Today I have a short topic to introduce to you related to something called vector math. We, in a prior video, have already seen that some quantities in physics have not only a size but also a direction associated with them, and the general name that we give to those quantities is the fact that they're a vector. If you recall, a vector is represented with an arrow, like so. And in our next unit, which will be on forces, we are going to have to pay close attention to the consequences related to vectors having direction. And that's going to lead to some special mathematical principles that we will need to apply in order to be able to fully understand forces, since forces will be vectors. So the first principle that we will be looking at is vector addition. Now you need to understand that in this course particularly, we will deal with cases where we will have vectors such as forces acting with or against each other both in one dimension as well as in two dimensions. So I have a couple of examples of how one-dimensional addition for vectors would work, and then a single example for how two-dimensional addition will work for vectors. So let's just focus our attention over to the left-hand side right here. When we have vectors that are acting in one dimension only, it's fairly straightforward. If the vectors are lining up, if they are adding together truly, in other words, my vectors are pointing in the same direction, whatever numerical value they have, they would add together. So in this case, I have 3 and 2 for my two vectors, and since they are pointing in the same direction, they will just add together to create 5. In my second example, you'll see that I have the same two vectors in terms of their magnitude. One's 3, one is 2. However, my vector with the number 2 is pointing in the opposite direction of my vector with the number 3. When my vectors point in opposite directions, it means that I am going to straight up subtract them instead of add them. So in this case, that would give me a total vector of 1, pointing to the right direction. Two-dimensional vector addition is a little trickier, and we're going to start bringing those ideas from when we did trig review to the forefront of physics. So here I have two vectors. One is a vector of size 3 pointing to the right, and the other one is a vector of size 4 pointing up. And I want to add these two vectors together. Now, unlike one-dimensional vector addition, I can't just add the numbers together. That's not how it works. Instead, I need to take these two vectors and I need to line them up so that they are what we call head to tail. In other words, the pointy end of the vector number 3 is touching the tail of vector 4. And what this will do is then show me what the addition would actually look like. And you'll notice that in the end, we've made a right triangle, where the legs are my original two vectors that I was adding together, and the hypotenuse is what we call the resultant, what we are getting as a result of this vector addition in two dimensions. And I could then figure out, well, what is the magnitude, what's the size of that resultant, in this case by using the Pythagorean theorem. So I would take my two legs and square them, add them together, and then take the square root, and that's how I figured out that, well, the magnitude of the resultant for these two particular vectors being added in two dimensions is 5. The last thing when it comes to vector math that we will need to be able to do is the opposite of adding two vectors together in two dimensions, getting a resultant, and that is breaking a vector into components. So here we are starting off with a single vector. In this case, it has magnitude 5, And you'll notice that it is a diagonal vector that points to the right and up. Now, most of the time in our problems, we're going to establish a coordinate system where we typically use the sort of axes that you would have on a piece of graph paper, where you have your x and your y axis. And in order to see how different vectors are going to interact with each other, we need to make sure that all of our vectors are either pointing only in the x-axis direction or only in the y-axis direction. Clearly, this starting vector is not doing that. So we are going to take this vector and we're going to re-represent it as a combination of two other vectors. One which is pointing just in the x direction and one that is pointing solely in the y direction. And the way we would then figure out, well, what is the magnitude for each of these two component vectors is by, again, using a little bit of trig. This is where we would use SOHCAHTOA to our advantage. So if I wanted to figure out, well, what is the x component vector down here, I could very easily say that, well, this, and I'm going to call it v subscript x, the x to tell me it is an x component, v subscript x would be equal to my original vector's magnitude of 5 times the cosine of theta. Theta being whatever angle I may have from my problem description. And then that would mean that my other component over here, which I'll call v subscript y, since it is pointing in the y direction, that could be determined by taking the magnitude of my original vector, 5, and multiplying it by the sine of theta. And if you want to know specifically where did I get this and this from, how did I know it was sine and cosine, feel free to ask me in class. It goes back to just using SOHCAHTOA, and I kind of rearranged it in one fell swoop. So if you just want to see a more explicit explanation for where this came from, feel free to ask at the beginning of class on Monday. That's pretty much all I have for you with regards to vector math. Just keep in mind that we will be using these principles during our unit on forces quite frequently. So until next time, physicists, until next time.